Quantum computing challenges the assumptions behind digital trust. RSA and ECC protect encryption, signatures, certificates, identities, and trust chains across today's systems. The concern is not only future access, it is also data captured now and evidence that must remain trustworthy for years. You've already built the core trust foundation: PKI, certificates, signatures, identity, KSI, eIDAS, and blockchain anchoring. Now the focus shifts from how trust is established to how quantum computing can undermine it, especially in public key systems that protect identity, certificates, signatures, and long-term evidence. This risk picture sets up the migration strategy that follows. Digital trust relies on public key cryptography behaving as expected. Today, RSA and elliptic curve cryptography are considered secure because the underlying math is impractical for classical computers to solve. RSA depends on factoring very large numbers. ACLI depends on the elliptic curve discrete logarithm problem. These assumptions protect web sessions, signatures, identities, devices, and financial transactions. Quantum computing changes that risk model. Algorithms such as Shor's could make these specific problems much easier to solve at scale. That is why post-quantum cryptography is not about panic. It is about preparation. A threat model asks 4 practical questions. Who is attacking? What can they do? What are they targeting? And how long must protection last? In the classical model, attackers are limited by today's hardware and known cryptanalytic techniques, which makes RSA and ECC expensive to break at useful key sizes. In the quantum model, the capability assumption changes. Algorithms like Shor's could make public key systems breakable once large, reliable quantum computers exist. So the question shifts from, is this safe today, to does this need to remain safe into that future? RSA appears in many familiar trust services, including certificates, TLS, email, software updates, and older enterprise systems. Its strength comes from a simple asymmetry. The public key includes a large number, n, created by multiplying 2 secret primes. Classical computers struggle to reverse that multiplication at real key sizes. Shor's algorithm changes the assumption. With a sufficiently powerful quantum computer, n could be factored efficiently, exposing the private key. At that point, encrypted RSA data may be exposed and signatures may be forged. RSA-heavy environments need inventory first, followed by a planned migration to quantum-safe algorithms. Elliptic curve cryptography became popular because it delivers strong security with smaller keys, keeping systems fast and efficient. That is why ECC is used across secure web sessions, mobile identity, digital signatures, authentication, certificates, IoT, code signing, and blockchain wallets. Its quantum risk comes from its reliance on the elliptic curve discrete logarithm problem. A sufficiently capable quantum computer running Shor's algorithm could solve that problem efficiently, breaking ECDSA signatures and ECDH key exchange. The challenge, then, is not only cryptographic, it is operational. Find every dependency, prioritize it, and replace it safely. Digital signatures depend on one critical assumption. The private key remains secret. If a quantum-capable attacker can recover that key, the trust model changes completely. They are no longer just modifying a file. They can create signatures that verification systems may accept as legitimate. Authenticity breaks because the claimed signer may be false. Integrity breaks because modified content can appear approved. Non-repudiation weakens because audit evidence becomes harder to trust. If the compromised key belongs to a certificate authority or intermediary, the damage can cascade through the trust chain. PKE works as a chain of delegated trust. A root CA signs an intermediate. The intermediate signs end entity certificates, and relying systems accept those certificates for websites, APIs, devices, and users. Quantum risk matters because each certificate is only as strong as the public key algorithm behind it. If that algorithm can be broken, attackers may impersonate identities or forge signatures. CA certificates are the highest value targets because one compromise can affect many downstream certificates. Resilience depends on shorter lifetimes, reliable revocation, timestamping, and the ability to move quickly to quantum-safe algorithms. For confidentiality, the risk often starts in the handshake. A client and server use public key cryptography to create a shared session secret, which then protects the encrypted TLS or VPN session. RSA key transport and elliptic curve Diffie-Hellman may be vulnerable to future quantum attacks. An adversary can record traffic today, store the handshake, and later use a quantum computer to recover the session key. The symmetric cipher may still be strong, but the key establishment has failed. That is why protocols need hybrid or post-quantum key exchange. Long-term validation asks more than whether a signature was valid on day one. It asks whether that fact can still be proven later, when someone challenges it. Contracts, medical records, audit logs, and government records may be reviewed years after certificates expire or algorithms weaken. Durable evidence preserves the facts around the original signing event: trusted timestamps, certificate status, revocation data, and archival records. The longer the retention period, the more important crypto agility and evidence preservation become. Consider a global manufacturer in 2026. Its R&D archives, VPN sessions, and supplier files are encrypted, so attackers cannot read them today. But attackers can still copy the ciphertext and store it cheaply. Years later, if powerful quantum computers can break the public key protection used to exchange those keys, yesterday's traffic may become readable. That makes quantum risk a present-day data governance issue. The highest risk information is anything that must stay confidential for a decade or more: secrets, designs, health records, financial data, and identities. Classify by confidentiality lifetime, not just by whether data is encrypted now. Long-term trust is about proving history, not only protecting secrets. Years later, an auditor may need to know who signed a record, when it was signed, which certificate was used, and whether that certificate was valid at the time. That requires preserving more than the document and signature. Keep the certificate chain, revocation responses, algorithm identifiers, timestamps, hash values, and the validation policy used. If signature algorithms weaken, external anchors such as trusted timestamps, hash chains, KSI, or blockchain proofs can help show that the evidence existed before any later compromise. Prioritizing quantum risk is not just a matter of finding cryptography. It means asking how long trust must hold, how exposed the asset is, and what happens if it fails. Root CAs and signing keys rise to the top because one compromise can break trust across many systems. Encrypted archives matter when confidentiality must last 10 or 20 years. Identity platforms and long-lived device credentials also deserve attention, especially when replacement is slow. A practical ranking considers lifetime, exposure, compliance pressure, and business impact, then moves the highest risk assets first. To build a PQC threat model, begin by locating every place quantum-exposed cryptography appears: RSA, ECC, and related protocols in certificates, VPNs, code signing, databases, and devices. Then identify what each use protects. Is it keeping data confidential, proving identity, preserving integrity, or supporting non-repudiation? Next, compare the required protection lifetime with the realistic migration window. Data that must remain secret for 10 years may create risk today. Finally, prioritize by impact, including long-term value, public exposure, and replacement difficulty. The result should be a ranked mitigation roadmap, not just an inventory. The key message is preparation, not panic. RSA and ECC still underpin PKI, signatures, certificates, and key exchange, but quantum capability changes their risk profile. Data lifetime matters because encrypted records and signed evidence may need to remain trustworthy for years. Durable validation depends on timestamps, revocation evidence, and strong anchoring. Next, we turn this risk picture into a practical migration strategy.